Hi, and we're going to continue our discussion about winds that develop in the mountains. And the first ones we looked at were thermally driven circulations. In other words, the heating and cooling of the mountains resulted in air that flows up and down the mountains and also up and down the valleys. Now we're going to look at synoptically driven flows. And what we mean by synoptically driven flows are, well, just as the name implies, winds that are driven by synoptic weather patterns. What do we mean by synoptic weather patterns? Well, that means basically the low pressure systems that develop and move across the United States. With them, strong pressure gradients you get also in the upper atmosphere. And as a result, you'll see high in the atmosphere jet streams moving over the mountains. So the combination of all the winds throughout the atmosphere result in the development of certain kinds of weather patterns over mountainous areas. So we're going to start by looking at the conceptual models. In other words, how do we envision what's happening over mountains as the air flows over the mountains? And it depends upon, of course, the wind. That's one factor, not only the wind direction, but also the wind shear and the wind strength. And we'll come back to shear later on when we talk about different types of waves. Also, it depends upon the environmental lapse rate, in other words, the stability of the atmosphere. And then finally, of course, it depends upon the mountain, and not only its size, but also its shape. So to start this idea or this the model discussion of our model, we'll look at kinetic energy and potential energy. I think most of you probably had this somewhere back in your high school training, maybe even in college you've had a course in physics. But you should know that, of course, kinetic energy is the energy that a body has because it's moving. In this case, we're talking about the wind moving, so that's your wind speed. And potential energy is the energy that an object has because of its height above the surface. Remember, or if you remember from your high school days, talking about dropping an object, how it accelerates, and the height of that object above the ground determines its potential energy. But also the stability of the atmosphere also has a play in the amount of potential energy that is available for a system. And I'll explain this here in a little bit. So first off, let's take a look at wind approaching a mountain. As the wind approaches the mountain, what is it going to do? Well, it depends upon how much kinetic energy that wind has, and also it depends upon the height of the mountain, which determines the air's potential energy, and also the stability of the atmosphere. The atmosphere tends to resist air that's going up if it's stable. So that also relates to the potential energy. So we're going to look at three different flows that can develop over mountainous areas. And this is actually a very complex mathematical or atmospheric science theory, but I'm going to try and break it down into these three basic types of scenarios. The first one means block flow, means that the wind approaches the mountains and is blocked. The second one, it goes, the flow follows terrain, means that it goes over the terrain and comes down on the other side. And then finally, the third one, gravity or mountain wave, is where the air kind of starts to oscillate downwind of a mountain. We'll talk about that. First, let's take a look at block flow. This is where the potential energy is greater than kinetic energy, meaning that the mountain is too tall for the air to flow up the mountain. It's just so high that as the air starts flowing up the mountain, it just runs out of kinetic energy. Or perhaps the stability of the atmosphere is so strong that as the air starts moving up, it just can't force itself up against the stable atmosphere, and it tends not to make it up over the mountain. So it gets blocked. In other words, the wind is not strong enough to make it up over the mountain, whether it be stability or the height of the mountain, or both for that matter. Or maybe it's the winds that are just so weak that they can't make it up, or a combination of those three factors. So that's what happens with block flow. Now with block flow, it blocks the wind on the upwind side, of course, and below, typically below the mountaintop. But above the mountaintop, the air may be flowing at a pretty good clip, And as a result, as it comes over the other side of the mountain, it'll follow the terrain. So that sometimes produces strong downsloping winds, and we'll talk about that when we get to the different types of weather patterns that develop in mountainous areas. Another conceptual model is the flow following the terrain, which means that the wind has great strength. It has lots of kinetic energy, and it has so much kinetic energy that it can overcome the potential energy represented by either the mountain height and or the stability of the atmosphere. So the third scenario that we can have is one which produces a wave, a gravity wave. And this happens when the potential energy is about the same strength as the kinetic energy. In other words, the air, the wind speed, is just strong enough to make it to the very top of the mountain. And that's about it. So how does it come down the other side? Gravity. Gravity pulls it down the other side. So gravity is our restoring force. The air is stable. It wants to come back down as a result of the force of gravity. So, of course, this depends upon the stability of the atmosphere. An atmosphere must be stable. Specifically, there might be an inversion right at the mountaintop to help enhance the stability of the atmosphere. So, of course, the air as it comes up, this is kind of just a step through and show you what a gravity wave looks like. The air, as it rises up over the mountain, it has enough kinetic energy, and as it hits the mountain, it starts flowing up the mountain. And as it rises, it becomes colder than the surrounding air. And colder air is more dense. And once it makes it just over the side of the mountain, over the top and down the other side, just starts to, gravity will start pulling it down because the air is more dense. More dense air means that it'll sink. The gravity is pulling it back down. So gravity is the restoring force. Finally, the air, as it sinks, it'll heat through compression as it sinks through the atmosphere, and it finally reaches the point where it had the same temperature as it began. We call that its equilibrium position. But the air has momentum, and it continues on, and it continues its downward trajectory until it compresses even more and becomes warmer than the surroundings. And warm air is less dense, and it will rise back up to the equilibrium. And this continues on, rising and sinking, expanding and cooling, compressing and heating, not heating, but actually warming. And it continues on until the wave is dampened. So with each oscillation, each time the wave goes through this oscillation, the height or the amplitude of the wave decreases. That's the basics behind the three different types of flow patterns, our conceptual model of winds that are synoptically driven. There's one more video in this lecture on synoptically driven systems, and that deals with climatology.